In the previous two videos, after convergence of the LMS algorithm, we have addressed the normalized version of the LMS algorithm. So let us have in this video the MATLAB demonstration for the normalized LMS algorithm, hence this topic. A very simple aim here we keep, so that is to write a MATLAB program to demonstrate the adaptive filtering using the normalized LMS algorithm. So here we have the MATLAB environment. We require untitled editor window. So here we take it, and now we shall have the first line commented to mention the purpose of this particular program. So I write here, this is a program for normalized LMS, standing for least mean square, algorithm. So for the algorithm, we have seen the update equation in the previous video. The LMS algorithm, conventional one and the normalized one also we have seen after the convergence. So here it is, first of all expected to have clear screen on the command window. Then whatever the variables you see in the workspace should get cleared, and the unnecessary MATLAB windows should be closed whenever we start executing this particular MATLAB script here. So for processing the signal according to the mathematical logic of the normalized LMS algorithm, we require the input signal. So as in the very first topic of the chapter, where we address the adaptive filtering with system identification, block schematics, I hope you recall, there it is desired signal and then addition of the noise to the desired signal, which is further processed, and finally we get the estimated signal, and the difference with the desired signal will be the error signal. So always and always the motivation is there to have minimization of the error signal here. So here we shall have the modularization, and this is for generating the desired signal, here. So for the signal to be represented onto the time axis here we define one time variable t that will start with the value 0.001 with the step size of again 0.001 up to maximum value equal to 1 here. And let us have the variable capital D defined, which holds the desired signal information, which is computed as twice of the sinusoidal function sine here. In the bracket we provide 2 multiplied to the constant pi, further multiplied to 50 and multiplied to the time parameter t here. So a periodic type of the signal here we have defined to be the desired signal here. Now after this desired signal, we want a signal to be corrupted with the help of noise here. So for that purpose, here we separate out a comment here, generating the signal corrupted with noise here. So as we have seen in the previous programming, the desired signal is added by the noise component of the random type here. So for that purpose, first of all we have to match the length of the desired signal and that of the signal corrupted with the noise here. So let us define small n to be the variable which holds the total count of how many elements are there into the desired signal. So for that purpose we have the MATLAB syntax NUMEL. The input argument is capital D here. We end this syntax with the help of semicolon here. Now the signal corrupted with noise. So this is the actual signal in practical sense here. So let us define it with the help of the variable name capital A. So it will be holding the desired information d of 1 to small n, the length, which is further added by, here we have the randomness added. So RANDN is the MATLAB syntax to generate the random signal. The dimensions to match with, we provide the input arguments 1, n here, and 90% of it we add to the desired signal component here. Now to develop the mathematical logic according to the normalized version of LMS algorithm, here we require a variable capital M to be holding the value 25. Then for the weight factors, we define the variable W, that is first of all initiated to have all the values 0 for the dimensions 1, capital M, ending with the help of semicolon. The update equation as it is there, that we have seen in the previous video. So there it is, updated weight factor. Here we define it with the name Wi here. So we also initiate it for the same dimension and the values 0 here. Then as we develop the further logic, it will be updated with the help of for loop here. Here we also require one variable capital E, that is initially empty here. The step size that we have in the conventional form of the LMS algorithm, so we keep it for this particular case to hold the value 0.5. Then as this is the normalized version of the LMS algorithm, the mathematical formulation you might have seen. So there it is, the use of beta, and this is further divided by the mod square of the quantity represented here. So for that purpose, here we will have definition of one variable called as DEN to represent denominator here. So mod square of the actual signal, here we compute it as A of, in the bracket, 1, all the elements, which is further multiplied to. So for multiplication we have the asterisk, the complex conjugate of the same. So A of 1, all the components here, all the coefficients. For complex conjugate I provide the apostrophe here, and here it is added by 0.0001 here. So this is what the denominator to implement the mathematical expression that we have seen for the normalized version of the LMS algorithm here. Next to that, here we take the help of for looping. Index variable I that will start at M will extend to small n here. Here we calculate capital E of I, which is initiated to be the empty matrix first of all. So here we have D of I minus the weight vector Wi, further multiplied to the complex conjugate of A of, in the bracket, here we have I with the step size of -1 in the decreasing sense. We have I minus M added by 1 here. So apostrophe for the complex conjugate ending with the help of semicolon. And the weight update equation, here we have Wi is equal to Wi from the above step, further added by twice of, here the multiplication is to the ratio. So what it was, the step size into the conventional form of the LMS algorithm, that we have written mu, which is divided by the denominator that we have defined in the above step outside the for looping here. This is further multiplied to E of I, further multiplied to capital A of I to -1 steps up to I minus capital M plus 1 here, ending with the help of semicolon and getting out of the for looping here. So that is why here it is the use of AND keyword here. So this is what the mathematical logic we have developed for the normalized LMS algorithm. The change you note down that here it is the use of denominator. So the variable DEN is there. So now we need to have estimation of the signal according to the normalized version of the LMS algorithm here. So I just mention a comment, estimating the signal. So in this case, initially we have the variable name est to hold this estimating signal. We initiate it with the values, all coefficient values 0 for the dimension n comma 1 here. Use of for loop, index variable I is equal to m to small n, where we define small j initially for the actual signal A, for I extending with -1 step, so it should be colon here, afterwards again colon up to the maximum limit I minus capital M plus 1 here, and then est of I will be computed here as the iterations of the for looping will be there. So inside the parenthesis here we have the weight update and Wi further multiplied to the complex conjugate of j from the above step here. So at the end we have semicolon getting out of the for looping here. So this way the estimation of the signal after filtering through the adaptive type by the normalized LMS logic we obtain here. Next to that, to determine the error signal here, so I write computing the error signal. So error signal is the difference signal. We hold the symbol capital E small rr. So here we have est apostrophe minus the desired signal D here. So this is what the script to generate the 4 versions. The first one, desired signal, 4 versions of the signal. The first one is desired signal, second one is the signal added by the noise, third one is the estimated signal according to the normalized version of the LMS algorithm, and lastly the error signal, which is difference of the estimated signal and that it was desired here. So here it should be all displayed. So I just write display of the signals. So for comparative display we shall be making the use of subplot command. We expect the 4 rows and only 1 column. Assignment to the first cell here with the help of plot command here. So the input argument will be capital D, so that the desired signal will be displayed in the first subcell here. We provide here a separate title to this plot. So the title, keyword, then we follow with a pair of parentheses and a pair of single quotes inside, and here it is the string printed desired signal ending with the help of semicolon. So out of the 4 cells into the pattern 4 rows and 1 column we have assigned to the first cell here. Next to that, by the sequence we are going to have assignment to the second cell. So it will be subplot within parenthesis 4 comma 1 comma 2, then again the use of plot command to make the display here. So here it is the signal which is having the desired signal component, the upper one added by the noise. So that actual signal we had denoted with capital A here. So here we provide the title, so within a pair of parentheses and inside a pair of single quotes here I write here signal corrupted with noise ending with the help of semicolon. Then it is the third cell here. So subplot 4 comma 1 comma 3 comma the use of plot command, where the estimated signal is to be displayed here. The variable name is capital E small st. So that is the input argument here, and the title here we provide estimated signal. This is the string we provide, or text you can call, and there should be the assignment to the last cell. So 4,1,4, the use of plot command, and the input argument is the difference signal, which is error signal. So capital E small rr, and here it is the title. So title is within a pair of single quotes inside the parenthesis error signal, ending with the help of semicolon. So this is what the MATLAB script here. Here we shall save it. So as we are into the chapter number 6 and 8th topic, I name it program _6_8.m will be the file extension. I save it to the current folder, which is called as MATLAB onto the desktop. I have created it, so I just saved it. You see, there it is, the file generated into the current directory. The name has also appeared to the tab on the editor window, and now it's time to run this particular program. So as I run this, there it is, a MATLAB window has popped up. So now I maximize this MATLAB window. You see there are 4 rows and only 1 column. In the first cell we have a plot of desired signal. You see the amplitude levels -2 to +2. At the middle there it is a 0 level here, and on the horizontal axis we have the interval 0 to 100, 200, 300 and so on up to 1000 as we have defined. So it was the definition of the parameter t, time parameter, starting at 0.001 with the same interval of 0.001 we extended to the value 1 here. So total 1000 samples here we have. So when the desired signal is added with certain randomness here, so we call it signal corrupted with noise, that we have denoted by capital A. So here it is in the second cell here. So we see a certain amount of distortion to the desired signal after adding randomness, and after getting this signal filtered through the adaptive type normalized LMS algorithm, here we got the estimated signal that is plotted into the third cell here, and the difference of the estimated signal and that of the desired signal is nothing but the error signal that is plotted into the last cell of this subplot here. So this was our topic, MATLAB program normalized LMS algorithm here. Now by the next lecture we shall continue into the same chapter, adaptive filters, and thereupon we shall be discussing one of the important application of adaptive filtering, that it is noise cancellation. So the next topic is noise cancellation. Thank you.